on Rn, n-dimensional space. So it is a common question. Why should we care about n-dimensional space? We live in a three-dimensional space. We mostly think in three-dimensional space. Why should we care about a space which has dimension more than 3? Say, why should we care about R4 or R5? So I claim that this A comma B can be written as a linear combination of these two vectors. Hello everyone, I am Shayok Chatterjee, an INSTAT second year student at ISI Kolkata. Today we will be talking about linear regression. We will start with some basic linear algebra and we will move on to linear models. Okay, let us start with a basic example. Suppose you have a set of red balls and a set of blue balls. Say, suppose you have some red balls and some blue balls, and you have a weighting machine. So you will use these balls to measure their weights and use those measurements to estimate the weights. So in the first measurement, suppose you take one red ball and say 2 blue balls, and the reading is say 4.1 kilograms. Okay, and next you say you have say 3 red balls and 4 blue balls. Suppose in that case the reading is say 9.8 kilograms. So based on these two values, you can directly solve the weight of the red ball and the weight of the blue ball. Sorry, mass. I mean mass of the red ball and mass of the blue ball, right? But suppose you have a third measurement. Suppose you have 2 red balls and say 4 blue balls again, and the weight is say 8.2 kilograms. Suppose you have this additional information. Now if you look into this problem carefully, you will observe that these are systems of linear equation. So you have 3 equations but 2 variables. The 2 variables are the weight of the red ball and the weight of the blue ball. But the values here, these are the measurements, they are not exact. Okay, so if you solve these 2 equations and get say some value of R and B, it may not happen that those values of R and B should satisfy the third equation, right? So these are approximate weights. So in each measurement, an error is associated. So in this type of problems, how can you estimate, say, the weight of a red ball or a weight of a blue ball? So we will look into this type of problems and try to answer these questions. So for these types of problems, we need a basic knowledge of linear algebra. So let us start. the fourth property is that the addition should be commutative. So what do I mean by commutative on that set F? Commutative means alpha plus beta is same as beta plus alpha. Okay. So this is commutativity. So these four properties are regarding the addition. So field addition should have these four properties. So these four properties are regarding addition. Okay. So if V is equipped with these types of operations, so we will call it a vector space. Okay, now let us discuss enough examples so that we are clear with the concept of fields or say vector spaces. Suppose you have the set of natural numbers with the regular plus and multiplication operation. So is this a field? So what if I put 0 additionally? Suppose I take n star, where n star is the set of natural numbers, and I throw 0 in. Then will it be a field? Suppose I consider a set S that is like this. Suppose it contains A, 1 by A, and these types of things, where A is a non-zero integer. So it contains all integers and their reciprocals, and say I add 0 additionally. So for each integer, its multiplicative inverse is there in S. Then will S plus dot be a field? Now note that if you add two rationals, you get a rational. If you multiply two rationals, you get another rational. The rationals, if you define this plus and dot operations, these operations are commutative and associative on the set of rationals. And there is an additive identity and additive inverse as well, right? And multiplicative identity, multiplicative inverse, and both the distributive properties. Just check that all the properties are satisfied. So we have a claim here. suppose you take this set 0, 1, 2 up to say m minus 1. Okay, and you have two operations, plus and dot. The plus is the addition operation modulo m, and dot is the multiplicative operation modulo m, right? Now this would be a field. This will be a field if and only if m is a prime. On R2, I have defined the regular plus and the dot. So let us move a bit forward and define these operations on Rn, n-dimensional space. So it is a common question. Why should we care about n-dimensional space? We live in a three-dimensional space. We mostly think in three-dimensional space. Why should we care about a space which has dimension more than 3? Say, why should we care about R4 or R5? So suppose for describing a particular entity, we require n things. For example, suppose think like that. Suppose you have a container, a cubical container, and gas molecules are floating inside it. Okay. So at each time point, you are interested in the coordinate of the particle. Let's say it is xt, yt, zt at time t. And you are also interested in the direction it is moving at that instant, right? So at time instant t, suppose it has a velocity vt, which has three components, say v1t, v2t, and v3t. v1t is the velocity along the x-axis. v2t is the velocity of the particle along the y-axis, and v3t is along the z-axis. So you are interested in this tuple, right? xt, yt, zt, v1t, v2t, v3t as a whole. So this whole thing describes the kinematics of that particular particle at instant t, right? So here you get an instance where it is not enough to consider only R3. Suppose for a particular individual, we want to measure n properties, and we want to represent all of the properties as a whole. Okay, then we need Rn, right? So I claim that this a comma b can be written as a linear combination of these two vectors. That is 1, 1. You can multiply it with some alpha. 2, 1. You can multiply it with some beta and add them up suitably. You have to choose alpha and beta suitably so that you get this a and b. Okay. I claim that you can find this alpha and beta. So this a comma b can be written as a linear combination of these two vectors. So why is that so? Let us move on to the problem we started earlier, problem with which we started. We started with this thing, right? That you have two types of balls, red and blue. You take 3 measurements and you get these numbers. So it is like, okay, if you summarize the things, what should you get? Let me go through the numbers again. 1 3 2 2 4 4. So it is like 1 3 2. This is a three-dimensional vector. R 2 4 4. B, you add them up and you get the vector of measurements 4,1, 9,8, 8,2. 4,1, 9,8 and 8,2. But obviously you cannot put an equal sign here, right? Because if r plus 2b is 4.1 and 3r plus 4b is 9.8, that is, if r and b satisfies the first two equations, that does not mean that r and b should also satisfy the third equation as well. So these measurements contain some measurement errors, right? So let us put an approximate sign here. So what is this thing? This is like taking linear combination of two three-dimensional vectors, multiplying it by the weight of the r balls, red balls, and multiplying this vector by the weight of the blue balls, right? So we are trying to write this vector as a linear combination of these two vectors. Now observe that in the three-dimensional spaces, if you take the span of these two vectors, if you vary r and b as all real numbers, you will get a plane that is spanned by these two three-dimensional vectors. It is like a plane in 3D, okay, spanned by these two vectors. Suppose this is the origin, but this vector is not lying in this plane, because if this vector was in this plane, you can find suitable r and b that exactly solves this system of equation. But since this vector cannot be written as a linear combination of these two, this vector is not inside this plane but slightly above, say, okay. So what you want to do, you want to find a suitable linear combination. Yes,
sir, why slightly above? I can't understand.
Because slightly above or below, not on the plane, slightly deviated from the plane. If it was on the plane, that vector can be written as linear combination of these two. Then you can find exact values of r and b, right?
Okay.
Suppose the first two equations give you some values of r and b that does not satisfy the third equation. That means this vector cannot be written as a linear combination of these two vectors, right? So this vector is not inside the plane that is spanned by these two vectors. So it is slightly outside. So what you have to do, you have to find the best possible linear combination, best in the sense that is as close as possible to this vector. You want to find a linear combination that is as close to this vector as possible, right? So you want to find this vector. Let us name it. Suppose this is 4.1, 9.8, 8.2. Suppose this is, say, y vector, okay? And you have these two vectors u and v. You want to find a suitable linear combination of say r times u and b times v, so that this is as close as possible to the original measurements, right? So you want to minimize the difference between these two, right? In some sense. So what is the difference between these two? Note that it is this vector, right? This
this height,
vertical vector, right?
this height should be minimized.
Right, this side should be minimized.
Yes, yes.
This side, let us mark it with red, say. So you want to minimize this, right? So for each linear combination, you join this tip with this tip and observe this distance. And you want to minimize this distance over R and B. R and B are your unknowns. You know U, V, Y. This R and B are your unknowns. So when this will be minimized, geometrically speaking, it will be minimized when this is the perpendicular distance, right? This is a point and you want to minimize the distance of this point and this plane. So if you want to minimize the distance, you should measure the distance perpendicular to the plane, right?
Yes, sir. Yes, sir.
Right. So this angle should be right angle. This should be a 90-degree angle, right? So this vector, this is the residual vector. So y is our actual data, and this is the linear approximation we are getting. So this is the residual, right? This is the residual, and we want to minimize the length of the residual. We want to minimize the length of this residual. And geometrically speaking, it is possible when this residual is perpendicular to this plane. In R3, the concept of perpendicularity is closely related to the concept of dot product, right? For people who know a bit of basic vector algebra, dot product being 0 means orthogonality, right? So this particular vector, this residual vector, should be perpendicular to the vectors in this plane. In particular, these two vectors u and v, they are in this plane. So this particular vector should be perpendicular to both u and v. This residual vector, right? So you get two equations: y minus r times u plus b times v. You take this linear combination, take the residual vector, and this should be orthogonal to u. So the dot product should be 0. And this should be orthogonal to v as well, right? This is the most fundamental concept of linear regression, basically. This should be 0. These types of equations are called normal equations. We will learn about normal equations in detail. So is this clear that these two conditions must hold? If we think in R3.
Sir?
Yes?
Sir, this y vector minus r u plus b vector, this is signify that height of the
right,
plane.
right. This is the residual. We want
Okay.
to approximate this y using the linear combination here. So
Yep.
this is the error we are committing in this approximation, right? This is the residual vector. This is the
Sir,
residual, right?
error should be always straight line.
No, not like that. Geometrically speaking, in this case, here the data is like a point here, right? And the thing we are trying to do is we are trying to explain this data as close as possible using this plane. Now, the thing we can do, we can get as close as possible. So we have to minimize, in some sense, the distance between this tip and this tip, right? So
Yes.
this is not error, actually. This is the residual. There is a difference between error and residual. Error is the measurement error. Say, suppose we are deviating from the actual measure here, right? From the actual measure, we are deviating a bit each time. That is what is error. That error is not observable because we only observe the measurements. We don't observe the error. This vertical line is the residual. This is the observed data, and this is the thing we are trying to explain it with. So how close are we to the actual data? So the difference between the observed data and the explained data, that is the residual. Okay. And the key concept here is this perpendicularity, that the residuals being perpendicular to those things with which we are trying to explain things. We are trying to explain using these vectors u and v, right? So is it clear?
Yes, sir.
If you have any queries, please let me know.
There should be a mod sign, right?
Uh,
Residual part.
Residual part?
Because that y can be upside and also downside.
Yes, yes, right. But we are measuring we are minimizing the length. It can be down here. Then this will be the residual, right?
Yes, so I think there length should be the mod sign saying.
Right, right. Length means always modulus. If you say about length, you take the modulus, or in some sense you take the norm, right? So you are trying to minimize the length, not the direction. You don't consider the direction, whether it is up or down. You just try to minimize the length. You have this plane, you have a point outside the plane, and you vary a point on the plane here, and you want to take this point suitably so that the point of the distance between this moving point and this fixed point is minimized. That will be when the moving point is directly below the fixed point, right? The joining line of the fixed point and the moving point is perpendicular to the plane. That is the most important concept here. So thinking geometrically will be of extreme help in regression problems. Thinking geometrically, thinking about orthogonality, about these perpendiculars and so-called projections. This is like the shadow of this external arrow is this arrow, right? If you drop light perpendicularly on this plane, so this is like the shadow, this is like the projection of this vector.
Oh, I have a doubt. So
Okay,
can you go
go
back?
on.
Yeah, yeah. So if they let's suppose now we have another color ball, let's say white.
Okay,
So then, in that case, we assume that it will span a basically a plane. So
right.
if we have another color balls, like suppose white, then what will be the
Okay,
it will be a basically a 3D plane, right?
right. Suppose you have a red ball, black ball, blue ball, and white ball. Okay. Now you have measurements, right? So how many measurements you are taking, that is obviously important. If you have these two measurements, you can solve these two equations to get R and B, exact values of R and B, not approximate solutions, right? The problem is when this third equation comes, you cannot exactly solve this system, right?
Right.
That was the problem. Now, suppose you have three types of balls, and you take measurements. Suppose A1, A2, B1, B2, C1, C2. Okay. So these are the measurements. These are the coefficients of the red ball. These are the coefficients of the blue ball. And these are the coefficients of the white ball, suppose. Okay. That is, you first take A1 red balls, B1 blue balls, and C1 white balls, and you get weight W1. Then you take A2 red balls, B2 blue balls, C2 white balls, and get weight W2, and so on, right? So suppose you have n measurements. So these are n vectors. These are vectors in Rn, right? So these three vectors, and if you are multiplying it with R, B, and W, which are unknown, which are the things we want to find out. So this is the, if you vary R, B, and W, you will get the span of these three vectors in Rn, right?
Okay.
So span of three vectors in Rn will be either like a three-dimensional space or a 2D plane or a single line. That depends on linear independence of these three vectors, right?
Correct.
Right. Now you have the whole span, and you have this measurement vector. This is not exactly equal to, but this is approximately. So again, you have an observation, and the span you can think as a space that can be a plane, a line, or a 3D space. But this vector is lying outside that space, right? Suppose this is V, and it is lying outside V. Again, you have to somehow find a point here suitably, so that the distance between the outlying point and the point inside that space is minimized. That is the residual, that is W1, W2. This vector, suppose let us call it Y vector again. Let us call it A vector, B vector, and C vector, right? So then you will try to minimize this thing. Y minus the residual will be R times A vector plus B times B vector. Sorry for that. These two are of same notation, and W times C vector. So you are trying to minimize the length of this residual. So we will try to minimize so-called the norm of this thing. Now, again, geometrically speaking, it will be minimized when this is perpendicular to this space. In particular, this is perpendicular to these three vectors, A, B, and C. Okay, so in that case, you will be getting three normal equations. Since you have three unknowns, R, B, and W. Initially, we had R and B, so we got two normal equations, right?
Right.
But if you have an additional ball, you will have to find an additional normal equation to solve the system. And note that the normal equations will be linear in R and B. Okay.
Okay.
These are linear equations in R and B. And if you have the third ball W, the third normal equation will be also linear in R, B, and W. So you just have a system of linear equations eventually. So finding a solution that is in some sense as close as possible to the actual data is nothing but solving a suitable system of linear equations.
Yeah, thanks.
Okay, fine. So any more questions?
So we are getting that vectors from the measurement, right? So
Yes.
so
Let me
if
go
by
back.
yes, if by chance, so if the measurements become such that the vectors become dependent,
If the vectors become dependent, exactly.
Yes.
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 Then that is a very good question. Then this projection will not be unique.
Yes, means for normal two variable equation, like if we
Right.
yes,
If the vectors become dependent, then the solution will not be unique. So we have to impose additional conditions so that the solutions become unique.
yes.
So in regression setup, this phenomenon is known as multicollinearity. We will talk about that.
Okay, means in simple word, we will come across later on about this, right?
Yes, exactly.
Okay.
We will discuss such issues when the things are not linearly independent and we come across problems.
Yes. And another doubt I have that here the number of measurements is setting up the vector space, right? Means dimensions of the vector space. I am not sure about it.
Right. If you have n measurements, you start working in Rn.
Okay, got it.
If anyone else does not have any query, then we can stop today. Thank you.